Basically, it's hard to find a date that's agreeable with everyone. And in fact, it's impossible because if I change the date, then it's going to conflict with somebody else's exam or project due date or whatever, you know. And so I have to get more feedback because there are people who are going to keep quiet, but you know, who have something like a test due on that date or something like that, and they're gonna complain about it. And so I'm not going to fix the date just yet, but either we'll leave the date the same or we'll change it. Now they were saying right after Thanksgiving, but right after Thanksgiving we have a test, you know. And so do you want the sulfate lab due, you know, the same day as the test? They said yes, you know. Or we have it before Thanksgiving, you know. But then some people said they need Thanksgiving to work on the paper the weekend. And so think about it and then give me your feedback, and then I'll try to accommodate as many people as possible for the due date on that. I mean, if the 30th, I was thinking October 30th, right before Halloween, would be okay. But, you know, in the past I've made it after Halloween, and people complain because they're going to go party on Halloween, so they didn't want to have to deal with the sulfate report. This is true. I had like 5 people come up and tell me that. So think about the due date. You know, personally, I don't care. I mean, we could have it due at the end of the semester. That's okay. I was thinking of having it done before. That way, you don't have to deal with the final and the paper at the same time. And also in the past, like for example, last time I taught this, not over the summer, but last time I taught this over the regular session, I had 2 formal reports due. I had this experiment as a formal report, which is the calorimetry experiment, and they had to do graphs, and they had to analyze it, and they had to talk about the theory of cooling, Newton's law of cooling, and all this other stuff. All right, and then I had the sulfate, and so they had 2 formal reports. So I thought, you know, since I'm only going to do 1 formal report this semester, we'll just have it due not at the end of the semester, but before the end of the semester. That way. But well, think about it, and then you know, you can come talk to me in private if you want, or you can post anonymously and just say, you know, you have other conflicts or whatever, and let me know. So I'll try to accommodate the majority of the people who let me know and work that due date. Now the other thing the afternoon class asked me yesterday was to move the exam date. The exam's on Tuesday, but they wanted it on Thursday. What happens is, if I move it to Thursday, then that compresses the time between exam 2 and exam 3, which makes it a little bit shorter. But, you know, the difference between Tuesday and Thursday is not that big of a deal. I could do that. So they wanted that. I could do that for you guys, too. But the problem is, again, other people might have big tests on Thursday, and they're hoping on Tuesday get the Chem over with and then take the other test on Thursday, since they might not be able to move it. And so you know, but those were the requests from the afternoon class that Adrian mentioned. That was it, I think. So I'll talk about that more as people look at their schedule. All right, today we're going to start off with doing some more calculations, digging out the system and the surroundings. So in the next experiment, actually these aren't in order, you know, but actually, how many calculations have we done so far? Two? Brian, you have a question?
I was reading over the procedures of the lab today.
Yeah.
Are we going to be using our TI-83? Skip that part of
He said he was using new electrons.
Yeah. I don't know if everybody caught that yesterday. No TI-83, right? We're going to use what? LabQuest 2. If you use LabQuest 1, it's a little different. It's all touchscreen. LabQuest 2.
You were using the new equipment?
It's brand new. And so this is why we don't have a written procedure, but it's so easy to use. You don't really need a written procedure for this. In fact, you know, I hate, well, I shouldn't say I hate, I dislike the the step-by-step, the mindless thing where you can go in autopilot mode and then just push the button. Okay, I got to push this button, I got to push that button, I got to push that button. And then pretty soon the procedure turns into a sequence of pushing buttons rather than, trying to figure out. And so this is why we're going to talk about data acquisition today, and how to set it up. Because data acquisition, it's the same for any instrument you use. There are certain parameters that you do, like, for example, resolution and bandwidth and those types of things. So we'll talk about that for this as well. But nowadays, these things are so user-friendly, it's not that difficult to get up to speed quickly. All right, the next thing we're going to do here is we're going to take 50.0 milliliters of, what was the molarity on the HCl supposed to be?
I think it was 1.00.
1.00?
I think so.
1.05, I think. 1.05 molar HCl. Plus, the other copycat is going to have the 50.0 milliliter of 1.00 molar NaOH. So, in this situation, it's easy to see what the limiting reagent is. What is the limiting reagent here?
We don't know.
You can eyeball it and then see. Can you eyeball it and just see what the limiting reagent is? Sodium hydroxide is the limiting reagent. They should react in a 1-to-1 mole ratio. Right, HCl plus sodium hydroxide yields sodium chloride plus water plus heat, right, plus energy. This is exothermic. And so we either do plus energy or we say delta H is less than 0. It's going to be a negative delta H, meaning energy is going to be given off. And so either of these two endings are okay. The top one is the Chem 4 ending. The bottom one is the Chem 1A, Chem 1B style. We don't need the plus energy anymore. We figure it out based on the delta H sign. All right, we're going to monitor both of these. Both of these solutions should be at the same temperature. Sometimes there's slight differences in the probe, the signal output from the probe, so sometimes they aren't reading the same temperature. Usually what you do is you check that. Actually, we're going to do this today. Oh, are we doing the old one? No, we're doing the new one. These are what the probes look like. Oops. Shoot. They have different things. The standard probe is a thermocouple probe where they put two different metals together and look at the resistance, how the resistance changes, based on the temperature between that junction. But this one has something else in here, and I read it, and you could read it about it too, but we don't need to know how it works. You just put this in. And so one of the first things we do is we check, are the two probes reading the same temperature? So we get a beaker of water and then just put both probes in the beaker of water and then see, are we getting the same? If not, usually what we'll do is we'll just calibrate it. When we calibrate the probes, the easiest way to calibrate these is like a beaker of ice water. Beaker of ice water should be at what temperature? 0 degrees. Because a beaker of room temperature water, we don't know which one is correct, right? One's reading 22.3, the other is reading 22.4. Which one's right? But if we have ice water, then we know which one's right. And then what we can do is we can offset the other one. But you know what? We aren't going to do that. We're just going to let it run and then just observe. Are they reading the same temperature? If not, it's okay. But we'll have one probe over here, the other probe over here. These are the probes. This is the data logger here. This is the data acquisition device. It's just looks like a PDA. It's basically just touch screen. There's a home button and then a left-right button here. But you can see it's pretty easy, the setup here on this, and we'll see that. 2. This is our stopwatch. The stopwatch gives people a lot of trouble sometimes. There's so many different modes on the stopwatch. The best mode is the clock mode, and then you can zero it easily, and then just start it. It's nice to have the clock there because you can kind of see sometimes if, well, actually, it's pretty straightforward. So you synchronize this. You know, we'll start data acquisition and the stopwatch at the same time, because here there's no stopwatch here. You know, there is a graph here, but you know, we aren't getting the count by second. And it's nice to know, especially when timing is an issue. So we'll be using this here. All right, so we'll monitor the temperatures, and this is just going to collect the data in a table. Sometimes what you can ask it to do is to put the data in a graphical output like this. And so hopefully the two probes are measuring the same temperature or pretty much close to it. So here, maybe we'll just do this. Two probes. And so we get data point 1. How long do we want to monitor the temperature for?
15 minutes?
Oh, a total of 15 minutes. About how long do we want to monitor the temperature as is, just sitting here before doing anything? 5 minutes. And so minute 1, minute 2. Do you expect the temperature to change much?
Nope.
No. I mean, these solutions are sitting on the hood over there. So we got the overlapping data here for the two temperature probes. All right, then what are we going to do? As we get to minute 6?
20 seconds before.
Yeah, 20 seconds before we're going to pop the lid off. So should we pour the acid into the base or the base into the acid?
The acid is the base into
No, remember double A. Double A is a safety rule. Have you ever heard of the double A safety rule? Double A means always add acids. Add acids. Add acids very slowly and carefully. So let's just follow that. In this case, it's no big deal because these concentrations are so small. You know, we don't expect much of a violent reaction, so it really doesn't matter. But when you get to high concentrations, you want to be careful. You want to add the acids to better control the reactions. Because even adding acid to water, concentrated acid to water, can generate a lot of heat. You don't want to add the water to the acid. If you add the water, this rule came about because people were adding water to concentrated sulfuric acid. Well, the drops of water that hit that sulfuric acid got so hot, they superheated and splattered everywhere. And when it splattered, you know, it makes a bubble of steam rapidly. When it splatters concentrated sulfuric acid on your hands or arms. So you don't want that. And also the test tube gets very hot. Whereas if we add the acid to the water, we add a drop of acid to the water, are we going to generate superheated steam? No, we aren't going to generate superheated steam because water has a very high heat capacity, and so it could act as a heat sink by controlling. And so that's the origin of the add acid. But here, we aren't going to generate much heat by adding. And so what we're going to do is we're going to pop the lid. We're going to add the acid to the base. Also, the base is the LR, right? The limiting reagent. The acid's the excess. So if we lose a little bit of acid, let's say we don't transfer all of it, is that a big deal? No, because we got some buffer, right? But if we transfer the base over here and some base is stuck on here, did we get complete reaction? We didn't. And so in this sense, it makes, you know, following our rule, add acids and the limiting reagent. Now, if the acid were the limiting reagent, then I would have added the base because I know this isn't going to produce a violent reaction. I would have added the base so I don't have to worry about losing a little bit here, right? All right, so we pop the lid off and then add, and when we mix two liquids, the liquids are going to mix more rapidly. And so we probably don't have to collect 15 minutes, but let's collect 15 minutes for all of these to be consistent. And so what's going to happen is it's an exothermic reaction, this acid-base neutralization, and let's say the purple we'll just have as this probe, and the black we'll have as this probe. And so we're going to stop following the purple because now the purple, once we remove the lid it's going to be measuring air temperature, right? Air temperature. And so we ignore that. Whereas the black now will be measuring the mixture temperature. And so we got a data point here, data point here. This should mix more rapidly. And so it shouldn't take as long to do what?
Like create
a smooth
curve.
cooling curve, right? Smooth cooling curve. What about these data points here? These first three, look.
We ignore them?
We ignore them. Why do you ignore them?
Because like it's happening.
Yeah, these are a result of thermal gradients, incomplete mixing. Right, that's good. You guys remember this stuff. And so what we're going to do is completely ignore those and then look at these latter points for extrapolation. Right? Oh, actually it came out close. And then we're going to extrapolate this. Now when we extrapolate this, we just average with 2 points and extrapolate. Or what are the two temperatures that we're going to get? Yeah, T initial and T final. In other words, the temperature of the mix and temperature. So I'll just call this T mix, T cold, or T, I'll just use cold. And so when we mix it together, all right, now we got to figure out what the system and the surroundings are. So we're going to have 100 milliliters of sodium chloride aqueous. Yeah. And there's going to be some excess HCl in there as well. All right, next, what do I do?
Determine the system and the surroundings and then write the formula.
Yes, determine the system and surroundings. Good. And so why don't you figure out what you want to call the system and what you want to call the surroundings? Erase this. We're going to use the first law of thermodynamics here. We're going to say that Q of the system is equal to minus Q of the surroundings. And so what are we going to define as our system?
The solution? The reaction?
The reaction, the solution, the mixture? The initial mixture? Okay, let's say we do the initial mixture as it. And so what are we doing? Are we is the system object, or is the system a reaction or process? Now, if the system is an object, then we're either taking a hot object and putting it in a cold surroundings, or we're taking a cold object and putting it into a hot surroundings. And then there's going to be heat transfer between the surroundings and the system. Is that what we're doing here?
No, it's a reaction.
What was the reaction? The reaction isn't, it didn't start off hot, did it? No, the mixture is at room temperature. The surroundings is at room temperature. And so we aren't dealing with objects here. The system is going to be the reaction. HCl plus sodium hydroxide. Now the reaction is going to produce some heat. That heat depends on the amount of reaction times what? Delta H or delta U in this particular? Delta H because it's at constant pressure. And so we're going to get the amount times delta H. The amount, we can figure out the amount in moles, because the limiting reagent was sodium hydroxide. We have 50 milliliters of 1 molar sodium hydroxide gives us 0.05 moles. 0.05 moles is also called 50 millimoles. So we have 50 millimoles of sodium hydroxide that we're reacting. That's the amount. Unlike the last one, which was grams. And then the surroundings, what is going to constitute the surroundings? The calorimeter. Calorimeter, which is the beaker, the sodium hydroxide beaker, and what else? Well, the rest of the universe is the calorimeter, basically. The calorimeter counts for the rest of the universe. What else?
The aqueous sodium chloride.
Yes, the aqueous sodium chloride, right. And so we need Q of the sodium chloride plus Q of the calorimeter. And that's it. And so Q of the sodium chloride, what is that? It's the amount. Well, how much do we have? We have 100.0 milliliters or 50 milliliters? 100.0 milliliters times C times delta T. All right, so we need C of the sodium hydroxide aqueous. Delta T is just T final minus T initial. We'll figure that out. For the calorimeter, what is it? Equal to? We only have one calorimeter. So C of the calorimeter times delta T. So we know the amount of sodium hydroxide. What don't we know? We don't know what delta H is. And so this is unknown. We don't know the heat capacity or the specific heat of sodium hydroxide AQ.
Do we assume that of water?
Yeah, we're going to have to make an assumption. Otherwise, we have to dig around and look it up. And so, since we aren't going to do that, we're going to assume that it's about the same as water. We assume that the specific heat of sodium hydroxide, not sodium hydroxide, this is not sodium hydroxide, sorry, sodium chloride. We assume that the specific heat of sodium chloride, AQ, is about the same as the specific heat of water. Why do we do that?
Because it would be really hard to try to find it out.
Yes, one, it was very difficult to look it up.
It's a good assumption.
Well, that's not that difficult to look up. We could look it up. But you'd also have to look up the...
temperature.
No. What do we know? This is milliliters. Specific heat is per gram. We would need to know the density. And so we'd have to look up the specific heat and the density of sodium chloride that's contaminated with a little bit of HCl. Is that easy to find? No. And so we aren't. So what are we going to do? We're going to assume one other thing. We're going to assume that the density of sodium chloride, AQ, it's dilute enough, is about equal to
Water.
the density of water. All right, the amount here, the amount is the LR. The LR is 50.0 milliliters of NaOH AQ times the molarity. It was 1.00 moles of NaOH per liter. And so this gives us what we call 50.0 millimoles, or 0.0500 mole of NaOH. And so we know how many moles of NaOH we have. Do we know C of the calorimeter? Yeah, that's what we're going to find out today. And delta T of the calorimeter is going to be the same as delta T of the mixture. And so we know everything except for delta H. What are the units of delta H? The units of delta H are going to be joules per mole. Joules per mole. Joules per mole, it's going to come out a big number, so we're going to convert it to kilojoules per mole. Since it's in the hundreds of thousands range. Around there. So I think we set up all the calculations. How many setups do you have for the calculations?
For the experiment?
Yeah, for the experiment. So we did water and water, two objects, right? Hot object, cold object, bring them together. We did water and water. We did solid sodium hydroxide and water. Is that two objects? Sodium hydroxide, solid, and water, mix them, reach some kind of middle temperature? No. That was a reaction and surroundings. And then we did solid sodium hydroxide and HCl. And then we did aqueous sodium hydroxide and HCl, aqueous HCl. Is that all of them? I think that's all of them, right? For Thursday as well. So for today, what we're going to do is we're going to do water and water. And what I want you to do is I want you to graph it and do the calculation before leaving in case you get a negative heat capacity of the calorimeter. You get a negative heat capacity of the calorimeter, something went wrong. And so I need to see what kind of heat capacity you're getting for the calorimeter. And so,
Water, right?
yeah, just water and water. So goggles you don't need today. And then, the earthquake drill is going to affect it, but these runs only take 15 minutes of data and then setting them up. So we should be able to get through it. Depends on how long it goes for.
It's on Thursday, isn't it?
Yeah,
No, Thursday.
Thursday.
We don't even have this.
Well, let me talk. Well, maybe I'll talk about it right now. During the earthquake drill, you're not supposed to get under these here. During the earthquake drill, the recommendation is either shelter in place or go to a wall. You know, stay away from, although those are safety glass, so those shouldn't scatter. But you're supposed to go to a wall and wait until the all clear sign signal comes up. Because these are load bearing. I mean, this is a load bearing wall here, although it's brick. So it might. Some of these walls are load bearing, means they're built a little stronger than a non-load bearing wall.
So we go to that wall.
Yeah. Anyway, if there's a fire, they recommend that you do not try to put it out. You just escape. You know, and when we clear out of here, we're going to exit and then walk over to the grass area over there. but they want the fire just to burn out in the room. And so these doors are like 4 or 6 hour fire rated doors. And so most fires will, once the fuel's gone, it'll stop. And there's not a huge amount of fuel in here unless it's a natural gas. But there's an earthquake shutoff for the natural gas over there. That's about it for the recommendations.
All right, when you graph these, we're going to use millimeter graph paper. And so we want to, how many squares are there lengthwise? I think there are 20 blocks lengthwise and like 15.
No idea.
And so we have
More than 20?
we have this for experiments. What do they call 2 or B?
Sermon
2 on. We're going to use this landscape orientation. For experiment 1, we're going to use a portrait orientation for this. Because the temperatures are going to be greater here. And what you want to do is use more than 50%. If your graph is less than half the page, then you could have easily doubled the scale. And so I'd mark you down for that. And then what you want to do here is this. We're going to have, blocks, and these blocks are going to have a grid pattern of 10 lines in both directions, I think. And so what you'll want to do is you'll want to pick the temperatures so that the scale's okay. Anywhere between 50 and 100% is good. And so don't pick weird numbers to use 90% of the graph paper. Sometimes people will pick like each block is 1.238 degrees C. And that's just too much hassle when you try to estimate here. And so we're going to plot the temperature here, and we're going to plot the time here. And so for this particular one, you could have split graphs where you know that nothing's happening here, so you can jump from, let's say, 30 degrees to 35 degrees and leave it blank, and split the graph. Have you done that before? But we aren't going to do that. You're just going to do this. You'll probably start off at 20 down here, and then depends on how hot your highest temperature is. If it's 80, then have 80 at the top, and then pick something equal. Easy, like 20, 25, 30, 35, something like that. And then we got to watch the hot water cool down. So oftentimes what people will do is they'll put the graph axis not on the edge, because it doesn't give you much room. You could write in the margin here, or you could, use a block and indent it like this. Either way, or you can use the margin here and write inside. But I'll leave that up to you. I don't really care. All right, so we follow the hot temperature, so at time 0, and we follow the cold temperature, say at time 0. And then we'll just make a plot. And so probably the easiest, since we might not have 15, I think we might have 15 blocks this way. But if we have 15 blocks this way, then each block is 1 minute. And so then we write out the data like this. And you want to highlight the data so it's easy to see. So most people just do an X or something like that and circle it. So when you do draw the line, we can easily distinguish where the data is and how your fit goes. versus some people will, what they'll do is they'll just draw a dot and then draw the line, and you can't see how many data points define that line. And so make sure your data stands out, whatever symbol you use to represent each data point. Okay, when we do the fit here, what we're going to do is we're going to do the best eyeball fit. It's not linear. You know, it's a curve. And so if it were linear, then we just get a ruler and draw a straight line there. But since it's non-linear, probably the best fit that you're going to do is just draw it by hand. We could do, actually, we're going to go into the computer lab. It depends on how much time we have today. But we can also graph these using Excel or some other graphing program. And then we can fit these to a nonlinear mathematical function here. Okay, and sometimes those fits will give you a better statistical fit of the data. Or we could use theory, you know, Newton's law of cooling. You could use that mathematical equation to fit this line and see how good that fit is. All right, so we do the fits here, and then we get the temperatures at 6 minutes. You know, we're going to have 3 temperatures here, T hot, T cold, and T mix. Once we get those 3 temperatures, then we're going to do the calculation. And when you're done with the calculation, I'd like to see the number, and I'd like to see your graph. The graphs, you know, should have labels on the axis, temperature in degrees C, time in minutes. You should have a title here. The title would be determining, you know, C of the calorimeter, something like that.
All right, are there any questions with this? Okay, then the equation I set up for you yesterday, it's different because how else did we change, for those of you who missed yesterday, how else did we change this? You could also see it on the video from yesterday.
How else did we change the lab?
Oh, we didn't.
We're putting cold water into hot water.
We're not putting cold water into hot water.
No, we are.
We are. Which is different from the lab because the lab procedure says to do what?
Put hot into cold.
Yeah, to put hot water into the cold water. All right. We could also have LabQuest graph this, but then you're missing. I want people to do at least one hand graph this semester, and the rest we can use this or use Excel. So what we're going to do is, although we could have LabQuest plot it and then fit the curves and do all that stuff, there's some advantage to doing it by hand, at least one. All right. You probably don't want to read. I gotta find this manual. Well, probably the easiest thing to do when I talk about the data acquisition is if you have this in your hand. And so why don't you, we're going to pair up, and why don't you go and check it out, and then I'll put up the PDF of the